Okay, in this screencast today, we're going to attend to this little area here of our table, which you remember we in the last screencast we caught up with where we're up to. So we're going to find the sum to the first n terms. We're going to find the nth term sum of a geometric, what's called a partial sum, because we are eventually going to look at infinite sums, but not in this lesson. Okay, so moving on to today's, we're looking at partial sums, or sum to n terms of a geometric sequence. Sum to n terms of a geometric sequence. Okay, so let's start perhaps with just looking at an example. So the example might be that we want to find the value of, let's say, 2 plus 6 plus 18 plus 54. So you can recognize a geometric sequence here. Let's take this all the way to 162, 486, 1458. All right, so find that value. All right, let's assign it. Let's call that my sum, S. Okay, now what we're going to do here is I'm going to, right, so we've recognized here that my value of R is equal to 3. So what I'm going to do, just bear with me, is I'm going to multiply this equation here, call it equation 1. I'm going to take equation 1 and I'm going to multiply right through by 3. Okay, now the reason for that will become clear pretty quickly, I think. So every term by 3, and you understand that that's a perfectly valid thing to do to an equation. Right, if I've got x over 3 plus 1 is equal to 12, I multiply by 3 and I get x is equal to 33, which is obviously correct. So this is a perfectly valid thing to do, and you'll see my rationale in a moment. Okay, so multiplying by 3, the first term becomes 6, the second term becomes 18, the third term becomes 54, the fourth term 162, 162 becomes 486. You can see that each term just becomes the term in front, the next term, 1458, except we get one more term on the end here, which is 1458 times 2, which is 4374. Okay, now that's going to be equal to, continuing our multiply by 3, 3s. I will call this equation 2. Okay, now what we would like to do, what we're trying to find is s. All right, so that's the goal, is to find s. And you have been faced many times in your lives with needing to find unknowns when you're given two equations. Hopefully springing to mind here is let's solve these simultaneously. Now, how? Now let's have a look at my terms here. I've got 6 and 6, I've got 18 and 18. So what I've got, if I do a subtraction, all my terms will disappear, will be eliminated, except the last term of my 3s and the first term of my s. So let's try that out. Let's try that out, see how we go. So what we'll do is take equation 2 and subtract equation 1. Let's see what we end up with. So we'll end up with, on the left-hand side, everything collapses, everything dissolves except the 4374. And I'm going to subtract, I'm going to take away 2, because that's all that's left in my s. And on the right-hand side there, I've got 2s. So therefore, 2s is equal to 4372, and therefore s is equal to 2186. So that's quite nice. Now, this would have been quicker just to sum these up. 2 plus 6 is 8, plus 18 is 26, plus 54 is 80, etc. Much quicker than doing all this. However, if we're looking at large partial sums, 20, 30, 50, 100 terms, obviously this is going to be quicker. and then when we start to look at infinite sums, clearly this is going to help us finding a method here that solves sums for us without doing it sort of manually each time. So let's look to generalize this result. Let's look to generalize. So to generalize, so rather than start with a specific example, let's go to our general sum, general geometric progression. So start with u1. Our next term is u1 times r. Our third term is u1 r squared. Run a few of these through just so that we can see how it rolls out. Okay, so what we're going to do is roll this right out to n terms. Now the nth term is ur to the n minus 1. I'm going to go to the one before that. u1r to the n minus 1. So that's my n terms. You can see I started at r to the 0, ended up at r to the n minus 1. So that's n terms. So that will be my sum. That's Sn. Okay, now let's do what we did in the example above, and let's multiply everything through by r. Now you'll see that, as happened in the last example, we're going to nicely eliminate a lot of equation subtraction, a lot of terms, sorry. So the u1 becomes ru1, u1r becomes u1r squared, u1r cubed here, etc., etc. Now when we get to this term here, u1r to the n minus 1 times that by r, we get u1r to the n minus 1. And then the last term there, when you multiply it by r, just raise the power by 1, and you just get u1r to the power of n. This is my Rsn. Alright, equation 1, equation 2. Okay, so let's now do as we did before and take equation 2 and subtract equation 1 and watch the results. We're going to get, so we're taking the second equation, subtracting the first. This term here is left. He's got nothing to simplify with in Sn. However, u1, this term here, u1 r to the n minus 1, there's one there, so they're going to eliminate, and that's going to work its way all the way down the line. They're going to eliminate, they're going to eliminate, they're going to eliminate each other. Now, I wrote that one as ru1 rather than u1r. Sorry about that. Okay, so as happened in the specific example, we are left with u1r to the n subtract u1. On the left-hand side and on the right-hand side, I've got Rsn minus Sn. So this is quite a nice little result. Let's tidy this up, because what I'm trying to find, what I want is Sn. So let's switch sides. I'll get Sn, and I'll factorize it out of r minus 1. You can see that the right-hand side just factorizes to that. And in fact, this side here will also factorize. I've got a u1 that's common, and I can put r to the n minus 1 in a bracket. So my last move is to make Sn the subject. The sum to n terms, u1 r to the n minus 1 over r minus 1. Beautiful. Or if I just multiply by -1 on -1, sometimes it's far easier for us to switch to that, and you'll see in a moment. What we want to do basically is keep the denominator positive. So if r is greater than 1, we would use this one. And if r is less than 1, we'd use this one here. Okay, so let's check this result with the example we did a moment ago. So for what did we do? We did 2 plus 6 plus 18, and we did that all the way to 1458. And we wanted that sum. Now, in order to find the sum, we need to know how many terms we have. So what term is 1458? So the first thing we need to do is go, all right, what's this? What's this is my un. I know that's u1 r to the n minus 1. that's 1458. I need to know what n is. I'm trying to find n. Okay, so u1 I know, that's 2. R I know, that's 3. I'm just trying to find n. So if I run this through, I should be able to establish what n is. I know that this is going to be n is an integer, so I'll be able to use I'll just be able to use a trial and error scenario, 729. So I know that 3 to the power of 6 is equal to 729. So I can say that n is equal to 7. So I have 7 terms. Go back to, all right, so this was all about just finding out how many terms I had. I now need to find this sum here. So using my newly found formula, which says Sn equals u1, I'm going to use the r to the n minus 1 because r is greater than 1 over r minus 1. Let's have a look at this. u1 is 2, r is 3, n is 7. Right? R minus 1 is 3 minus 1, which is 2. Cancel, cancel. I end up with 3 to the 7 minus 1, which is, of course, 2186. So it all checks out. My formula works. Okay, so here we go. We can now go back to our notes, and we can fill in that this sum to n terms here is u1 r to the n minus 1 over r minus 1. Now I'm going to, there is one more. We need to find our infinite sum for a geometric, so we're going to leave space for one more geometric result here, but that fills in the table so far. Okay, let's have a look at another example. Okay, so an example, find the sum. I should just write this out. Okay, so in this example, and this is often how it's written out, we're just given the first few terms so we can establish what our value of r is. So in this case, our value of r is 2, our u1 is equal to 3, and we want the sum of the first 5 terms. So S5 will equal u1, which is 3, by r, which is 2 to the power of n, which is 5, minus 1 over r minus 1, which is 2 minus 1, which is just 1. So this is going to work out nicely. It's just 3 by 2 to the power of 5, which is 32, minus 1 is 31. So our sum is 93. Now our geometric sums are often quite large. This one was kept under wraps because we only looked at 5 terms. So that's one example. Let's have a look at one more before we do a couple of questions. Okay, our friend sigma notation pops back out, of course, because we're talking about sums, and this is our shorthand way of writing sums. Right, so what do we do with sigma? I always think it's a good idea to just roll the first few terms out. I can see what my value of r I shouldn't use. This is why the textbook have used I, because r is, let's just use, it doesn't matter what letter we use, but not much, a bit confusing to use r because r means something else to us. It's our common ratio. So so the best thing to do here is, with any sigma, is to roll it out. Now I can see, because a half is my base, that's going to be my value of r. But let's just verify. So 2 times, my first term is 2 times 1/2 to the power of 1. My second term is 2 times 1/2 to the power of 2. You can see that each term is being multiplied by a half. My third term is 2 times 1/2 to the power of 3. You get the idea. And we're going all the way up to the last term. All right, so we get 2 times a half, which is 1, plus 2 times a half squared, which is a half, plus 2 times a half cubed, which is 2 times an eighth, which is a quarter. So this is going on. And our value of, let's pull out our values. Here's our u1. R is equal to 1/2. And n, always easy to see with sigma notation, is 7. Sigma notation is really, really helpful. Lots of information comes out in sigma notation. So therefore, my sum of 7 terms is going to be u1, which is 1, times r, which is a half, to the power of n. Sorry, I know what n is. It's 7, minus 1 over r minus 1. Now, r in this case is a half, so I'd actually go and use my other formula, which reads u1, which is 1. Now I'm going to go 1 minus r to the power of n over 1 minus r. Now, the reason I've done that is to keep the denominator positive. Again, I know what n is. It's 7. Okay, so this just needs to be run through the calculator. I'll do that. Actually, I'm just going to do this by hand because the calculator will approximate this to a decimal. So I'll forget about this 1. I've now just got 1 minus, now a half to the power of 7. I know that 2 to the power of 7 is 128. So that's going to be 1 over 128. And that's all over 1 minus a half, which is just 1 half. Now my numerator, therefore, is 127 over 128. My denominator is a half. If I divide by a half, it's the same as multiplying by 2. So I get 254 over 128, which reduces to 127 over 64, which might be about the best we can do. Okay, I think you should now go and do questions 9 and 10 from exercise, which one are we doing? 1C? Okay, then come back and we'll do one more example and I'll let you loose on another couple of questions. Okay, one more example, the sum of the first n terms. So another one of these questions where we're given the sum of the first n terms rather than the nth term sum. And from here, we need to find the first term and the common ratio of the sequence. Okay, so what do we do in these situations? We just find S1 initially, which is just 7 to the power of 1 minus 1, which is 6. So that must be our U1. Find S2. That's the next thing to do. What's the sum of two terms? 7 squared, 49. 7 squared minus 1, which is 48. So therefore, U2 plus U1 have got to equal 48. So U2 is equal to 42. Okay, get one more term, 7 cubed minus 1, which is 49 by 7, 343. So that's 342. And so that means that U1, 6 plus 48, 54. Plus 342, so U3 must be equal to, where was I, 54 to 342 gives 288. So what is going on here? Let's find out what our R is. Our R, remember, is any term divided by the term in front. So what I've established here is a sequence that goes 6, 48, 288. Sorry, not 48, 42. That was my sum, 42 to 88. So I should be able to now just take 42 and divide by 6, which is equal to 7. I should be able to take 288 and divide by 42. Sorry, mistake. This is 294 here. Something wasn't quite working out there. I was taking 42 rather than 48. So to get my third term here, I needed to take 342 and subtract 48. That gets me 294. So 294 goes in here for my check. 294 divided by 42 is 7. So my R is equal to 7, and my first term is 6. U1 equals 6, R equals 7. Let's now go and do questions 12 and 14. So from 1C, let's do 9, 10, 12, and 14. All right, I'll see you soon.